Hello, Professor. My name is Jasleen Gorsaini and my student ID is 101486141. So, this is my assignment 3, and here I have two parts, part A and part B. So, for my part A, I have imported all of these NumPy, PIL, scripts, schemate, all of these here. And then here in this cell, it downloaded the image from the URL using the request library. Here it prints the raw binary content of the response, and here we convert the raw image data into NumPy array. So this is our first image. So this plots the image using matplotlib. We can see the original color of the image here. And then in this part, this prints the shape of the array. For example, something like 225, 225, 3, meaning the image is 225 pixel tall and it is uh, somewhere around 225 pixel wide and has three colors and channel, red, green, and blue. Then here as we go, this is where here we keep only channel 0. Here we only keep channel 0 as this is which is red channel, and override the variable. From this point we only work with this single channel, the 2D grayscale like version of the image. And then here this just display the raw numbers inside the array. Here we apply the convolution manually. First, we pad the image. This adds the border of the zeros around the image so the kernel can slide over the edge properly without losing the pixel. Then here it confirms the padding worked. The padded array is 2 pixel tall, uh, 2 pixels larger in each direction compared to the original. And for this, this is the actual convolution operation. The the two for loops slide kernel across every position in the image. Then this is our result. The result looks the same as the original because the identity kernel doesn't change anything. This was just a demonstration of how convolution process works. Then this is this helper function crams any pixel value to stay between 0 and 255 pixel. So here, this function wraps everything we just did manually into reusable function, our line. So this kernel detects horizontal lines. The middle row has two positive values like 2, and top and bottom rows negative minus 1. So whenever there is a strong horizontal edge in the image, meaning a bright row between dark row, the result will be a higher value. Then here for question 1a, I created the kernel to detect 45-degree diagonal lines going from bottom left to the top right. Then for my question 1b, I created a kernel to detect 135-degree diagonal lines going from the top left to the bottom right. This time the two S are placed along with the main diagonal of the kernel. Then for my this question 2a, for this one I applied the kernel to the image. this kernel detects the edges at the corners. It responds strongly where there are diagonal intensity. You can change. And for my 2B, this is the Laplacian kernel. It detects edges in all directions at once. The center value is -4 and four neighbors are 1. For 2C, this is an enhanced version of the Laplacian. The center is 8 and the surrounding is 8 pixels surrounding with like -1. It's more aggressive than the previous ones. Then this is my part B. Again, I imported all the libraries which are needed. I loaded the data set and I started building our neural network over here. So the original model, let me explain. The first layer, which scans 32 by 32 image with 32 different 3 into 3 images. Each filter learns to detect a different feature like edges or colors. Padding same means the output which stays the same as the input. The layer 2, which is max pooling 2D, this reduces the feature map size by half. Then the flatten one, the flatten one, um, it is fully connected layer. Every neuron connects to every value from flattened layer. And the dense with 10 neurons, this neurons and softmax. So this is the output layer. It gives the probability for each layer, like each of the 10 cipher 10 classes. So we compile the model with the Adam optimizer, which adjusts the learning rate automatically. The loss function is categorical, the standard choice of multi-class classification. For the custom callback, so this is the custom callback that prints the training and validation accuracy every 5 approaches. And for the training of the neural network, this is where we train our 50 approaches with the batch size of 256. And this is our result, which shows us. Then for our question 4, um, the model has already 5 layers. Conv 2D, max pooling 2D, flattened, dense with 128 neurons, and dense with 10 neurons. For question 5, um, for our question 5, I've already explained what each layer does. Conv, it attracts the features from the image. Max pooling reduces the size to keep the only strongest feature. Flatten converts 2D to 1D. Dense 128. It is a feature which learns patterns, and our dense 10 outputs the final class probability. Question 6, I added 2 more convocation layers. The new model has 3 convert to D blocks. Then for my question 7, so comparing our original model to the deeper one reaches higher training accuracy, which shows us it has more capacity to learn. However, the overfitting is also more visible. The gap between training and validation accuracy is larger. For question 8, I added the dropout layer with the rate of 0.5 right after flattening the layer. And for my question 9, the dropout randomly turns off 50% of the uh, neurons during each training step. So at very batch, a different random half of neuron is ignored, which focuses forces the network to not depend too much on a single neuron. It has to spread knowledge across many neurons. Thank you.